Hi, I am Neil Anderson. I am a current student in Math 124, and today I'm going to talk to you guys about graph theory. Now, when we're talking about graph theory, we aren't talking pertaining to charts and whatnot. We're talking about something a little bit different, and I'm going to be going over that and showing you guys exactly what that is. So, just to give some definitions here, a graph consists of a set of vertices and edges that join in pairs of the vertices together. Graphs are generally represented with capital letters, such as a capital G, or you could say a capital A. We won't use lowercase letters. In my examples here, you'll see lowercase letters, but we generally don't use those when we're talking about graphs. Now, to start off with our first definition that we really need to focus in on is a loop. So a loop is a edge that connects starting with one vertice and ending at the same vertice. So for example, we'll start with P here. It would go just like this, and it would start at P and end at P. And that's all that a loop is. And so I'm going to erase this real quick, get that out of the way, and then we'll get P back in there. Now the next thing that we're going to talk about is a walk. So a walk is a finite list of alternating vertices and connecting edges that begins and ends with a vertice. So for an example, as far as what a walk is, a walk would be considered something like this. So we go from A to P, and then from P to C. Now, this is not a walk itself. Just because they're all connected together doesn't mean that it is a walk. They all need to be connected together. And so in order to complete this, we're going to go from C to P. All right. And that would connect. And so A would not be included in the walk. It would just be P and C. That would be the walk right there. Now we're going to talk about connected and disconnected graphs. So I'm going to erase some of this real quick, and we're going to get this out of the way. And so disconnected graphs, they are connected if at least one path connecting each pair of the distinct vertices. So in order for them to be connected, it needs to go from one to another, basically. And I'm going to show you guys this in the next example here. I just need to get the letters back in real quick. All right. And I know that was P in the middle originally, but we're going to change it to K. And so we're talking about connected and disconnected vertices here. So for example, to start out, we're going to say that this is all part of one graph. And we'll say that A and K are connected, and it's also connected to M and back over to A. And then we will have P and L. That'll be another one. So A, K, and M are all connected to each other, but K and P are not connected. That would be a disconnected graph. So the example on the left is a connected graph, but when we bring in the right side, it becomes a disconnected graph, if that makes sense. Okay? So once again, we have to go back, erase everything here real quick. All right. All right, and then we're just going to drop those letters back in real quick, and they're going to be different letters, and that's okay. But this is just for an example to give you guys a little bit more of an understanding of what's going on as far as it comes to graphs. And so we're just going to go over a few more things, and then we're really going to get into the meat of this, which is the Euler's concept. which is interesting because it's one of those puzzles that I did as a kid when I was growing up, which I just thought it was really interesting to see that come back and play a role in the math class that I'm taking now. So we have all of those. Okay, so we're going to talk about first adjacent. Two vertices that are sharing an edge are adjacent. So, for example, if we were to run a line or an edge from G to J, that would be two adjacent vertices. Now, when we talk about incident, those are two edges that have a same vertice with one another. So if we run a line from G to J, and we'll call the line line exclamation point, for example, and then we will call this line over here line 4. All right, and I'm just going to run a line or an edge between these. So we have edge exclamation point and we have edge 4. The edge exclamation point and edge 4 are related to each other, making them incident because they are sharing a vertice on J there. And then the last thing I want to talk about is a path. A path is a walk with no repeated edges or vertices. So when we go to do a path, for example, and I'm going to bring this up on a different one because I have it set up already. This is the puzzle that I'm talking about with the Euler's circuit. The Euler circuit, you need to make sure that you do not run over the same edge that you started with, or not the same edge that you started with, but you can't repeat the same edge. And we're going to start at point C, or vertice C here, and we need to end at vertice C. So to start out, we are going to run up from C. And this, you can't lift your pencil when you do this. And so we'll run over to B, and then up to A, and then back down to B, and then down to F, up to B, down to D, and then we'll go from D to F, and F to C. And we started back at where we started at. So that's just one example of an Euler's circuit. There are examples of an Euler's path, and that's where you tend to cross back over lines. But that's what an Euler circuit is when it comes down to it. A lot of people, when they first see it, they announce it Euler's circuit. It's pronounced Euler's. It's kind of a weird spelling. So now we're going to go ahead and do two problems from the book. All right, and I have two picked out already, and I'm going to type them up as we go. And so the first one that we're going to do is going to be, and we'll just zoom this in here real quick, is going to be number 11 on page 735. So it says we need to list the vertices and edges of each graph. So to start out, it's USA, and then over here we have Mexico, and I'm just gonna shorten these up. We have the UK, we have Canada, and then at the bottom we have Algeria, and then between these they are all connected with edges. So I'll just run edges to each of these real quick. And then this one for Mexico is only connected to the US. And so this edge right here is 3. This one is 10. We have 60. And then we have 2. And finally, we have 1. So it says to list off all the vertices and all the edges for each graph. So with this graph, our vertices would be the US, and I'm going to highlight these in a yellow. If I can grab my highlighter here. It's not going to let me. So we're just going to airbrush over them. We have vertices right there, which is US, Mexico, Canada, Algeria, and the UK. And then we will highlight in red our edges. So our edges are 3, 10, and 60, 2, and 1. All right. So those are our edges. And once again, those are 3, 10, 60, 2, and 1. Our vertices are Mexico, Canada, Algeria, UK, and the US. And that was number 11 on page 735. The next problem that we are going to do is going to be identify a cycle in the following graph and determine its length. So cycles is having it go from one vertice to the next vertice, and I will be able to show you this on paint here, so give me 1 second to pull that up. So this is what it looks like in the book, and I need to type these in here real quick. And so it's just one giant circle, and believe me, my drawing's not the best, so forgive me for that. Looks like a pretty straight circle to me, or close enough. So it's just a circle going around. And I'll kind of make little dots at least where we have our vertices at. Let's see if we can bring in a different color here. Put them as red dots, that way we know. And so when we do a cycle, we are looking to identify the cycle for, and we'll call this graph J, okay? So the cycle is all of the way around, all right? And so it says a cycle is a closed walk that is a cycle that starts and ends with the same vertice and has no edges or vertices repeated except for the starting vertex. So we'd start at vertex R and then go all the way back around to vertex R. And so the vertex, the total cycle would be, we'd have one, we'll label this line, or this edge 1 right here. Sorry, I'm having a hard time talking. And then this is going to be 2. That's 3, 4, 5, and 6. So the total cycle for this would be 6 because we are counting the edges in between each vertex as one part of the cycle. So 1, 2, 3, 4, 5, and 6. The last thing I want to cover real quick before we go here is degrees. So we're going to go back to the problem that we did off of page 235. And we'll talk about degrees here. So with the degree is how many edges are coming into one vertice. So for the US, we would say, and what's something that's really easy to do is just to cover up and just look at the US. Don't worry about the rest of the graph. And so we can do this real quick just to make this easier. And you can see, okay, we got 3 points or 3 edges coming in to the US. So we would label that the US has 3 edges that come to it. Mexico, if we look at that, it only has a degree of 1. So that would be a 1 degree. And then if we look at the rest of them, they're only going to have 2 degrees. So the UK is going to be a 2 degree, Canada is going to be a 2 degree, and Algeria is going to be a 2 degree. Guys, I hope you found this helpful. Thank you for watching, and I hope you have a great day. Bye.